Jai Hind everyone. I, Suvarna Mujumdar, welcomes you on a lecture on binary counters. First of all, we will discuss what is counter and then how we will design this binary counter if a number system is given to us. So counter is nothing but a digital circuit which is either a asynchronous in nature or synchronous in nature, and we have both type of counters, and these counters are used to count the events occur. So the binary counter is nothing but a group of flip flops connected in a sequence way so that it can store the number of event occurred. Now, as I told you, there are two types of counter, the asynchronous counter and synchronous counter. So, depending on the requirement, we will design a binary counter that if we want an asynchronous counter, then in that case, the clock applied to all the flip-flops are of different in nature. But in case of synchronous counter, the clock applied to all the flip-flops are of same frequency, or we can say we can apply same clock to all the counter. So let us take the size of a counter. So if suppose binary counter, we have to design a binary counter, then in case of binary counter, either an n bit is given to us, that we have to design an n bit counter. So let's take an example that if we have to design a 3-bit counter. Now if we require 3-bit, we have to design a 3-bit counter, then we require 3 flip-flops. So the n bit, it will define the number of flip-flops. Now, as we know, there are 4 flip-flops: SR, JK, D and T. So, while design a counter, which flip-flop we will choose? So, if we have to design a counter, there are 2 options we can choose. Either we can go with JK flip-flop or we can go with T flip-flop. So, either JK or T flip-flop. Generally, we prefer T flip-flop to design a counter. Whether it is an asynchronous or synchronous, we use T flip-flop, as in case of T flip-flop, we have option that when we apply 0 as an input to the T flip-flop, the result will not be changed, it remains the same. And when we apply 1 as an input to the T flip-flop, the output toggles. And in case of counter, we want that for each clock pulse, the counter counts a 1 bit. So, for each clock pulse, we want that counter should be toggled or go to next state. So, here for 3-bit counter, we will use 3 T flip-flops. Now, we have to decide the sequence for the counting sequence, that how it goes to start. So, depending on the counting sequence, there are again we divide the 3-bit counter into 2 types. One is the up counter and another is the down counter. In case if we decide that we have to design an up counter, then in that case the sequence will be, it start with 0 0 0 and it end till 111. That it will count from 0, 1, 2, 3 like this. It will goes up to 7. As with 3 flip-flop, we will represent 8 states. And if we go with down counting, then we will start with 0, 0, but the next state will be 111, and from 111 it goes to 0, 0, 0. Like 7, 6, 5, 4, like this it goes to 0. So, we have, it is a down counter. So, now we have to decide whether we have to go with up counting or down counting. If in a design problem statement, if it is given that we have to design a 3-bit up counter, then in that case our sequence or state diagram will start with 0, initial state will be 0, and then it goes with 1, 2, 3 like this in a sequence, and it come back after 7, it again come back to 0. So, state diagram is the way we can represent our counter. So state diagram for 3-bit counter, we start with 000, we goes to 001, then 010, 011, 100, 101, 110, 111, and again we will go to 000. So in this way we can say it is an up counting. Now if we say we have to draw the state diagram for down counting, so down counting it will goes like this. 7, 6, 5, 4, 3, 2, 1 and then 0. From the same counter, we can either go with up counting and down counting, and if we have to use same 3-bit counter to go for up and down, then in that case we need a control signal, and the value of this control signal, suppose C is 0, we can say it is an up counting, and C equals to 1, it will behave as a down counter. So we need a control signal, or we can say an enable signal, which can enable the functionality of our 3-bit counter. Now while designing a 3-bit counter or a 4-bit or 5-bit, the process is same. We have to first decide the state diagram for this 3-bit counter, and then we will go for state table. So in case state table, now as I told, we have to decide, we use a C as a counter, as a value, that C is our input. Now we will have a present state. Then we will have a next state. And from this, we will decide the flip-flop inputs. So as I told you, while designing a counter, we will mostly choose T flip-flop. So we will take TA, TB and TC as the 3 flip-flops while designing a 3-bit counter. Now initially we consider C input as 0. Now our present state A, B, C, and next state AT plus 1, B plus T1. So it is 0, 0, 0. The next state will be 0, 0, 1. Now again if we pay 0, 0, 0, 1 is the next state, it will be 0, 1, 0. 0, 1, 0 is the state, then we will go with 0, 1, 1. 0, 1, 1, we will go to 3, 4. From 4, we will go to 5. 5, we will go to 6. 7. And from 7, we will again back to 0, 0, 0. So 0, 1, 2, 3, 4, 5, 6, 7. Now next we change the input. Now when we change the input, our initial value will be 0, 0, 0. So it will go to 111. Then again 1. So now it is not at 1. It will be at 111. So it will be 110. 110, it will become 101. Now 1015, we go to 4. Then from 4, we go to 3. From 3, 2. And from 2, 1. and from 1 we will go to 0. So in this way we will have a sequence from up counting and we will have a sequence for down counting in the same flip-flop. Okay. If only we have to design a 3-bit up counter, then we will go for up state table, and if we go for down counter, then we go with down table. Now, from this table, we have to refer the excitation table of T flip-flop to find the outcome. So, for excitation table, the excitation table for T flip-flop is QT plus 1 T. So if it is 0 0, T is 0, and if it is 0 1, T is 1. 1 0, T is 1. 1 1, again T is 0. So referring to this table, we will go for finding the value of TA, TB. So TA will be 0, 0, 0, 1, 0, 0, 0, and 1. Now in this case, it's again 1, 0, 0, 0, 1, 0, 0, 0. Now for this case, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, sorry, 0, 1, 0, 0, so 0, 0, 1, 1, 1, 0, 1, 1, 0, 1, 0. Okay. Now for the TC, we will go with 0, 1. So it will be 1, 1, 0, 1. So for TC, that is the lower, for LSB case, you see that for each input, the output is changing. So we can say for each case TC, it is 1. So toggling. Yes. So from here we obtain TA, TB, TC value, and if we write in terms of min term TA, so TA is 1. This is 1 for 3 and for 7, for 8 and 9, 10, 11 for 11. So TA will be 1 for 3, 7, 8 and 11. Now TB, for TB we will find the value that TB is 1 for 1, 2, 3, 5, 6, 7, 9, 11, 12, 13, 14. It's not 13, it's 10. 1, 0, 1, 0, it's 10. And it's 8 to 14, 13. So it's 13 and here it is 15. So we have to make changes here. We have to just we have to check here that here it is. We have to change this value. Here we have to check. It is 1, this 3, it's 5, and this is 7, this is 8, and this is what 4 times 1. So it will be 15. It's 14, 8 for 12, 13, 12, 11, 10, and this will be the 9. So now if we find for TA, this 7, 8 and this will be 12. So 3, 7, 8 and it will be 12. And for case of TB, it will be, here we will see 1, 3, 5. So 1, 3, 5, 7, 8, then this will be 14 and 12 and 10. 12 and 10. In case of TC, for all the values from 0 to 15, it is 1. Okay. So now we have to solve the KMF for these terms. So we will solve KMF for, we have to solve KMF for TA as well as for TB. So for TA, if we will solve the KMF, CA, B, okay, for confusion, we will take this as M. To avoid the confusion, we will take it as M, MABC. So 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0. Now for 3, it is 1. So 0, 1, 2, 3. Then 4, 5, 6, 7, 7, it is 1. 8, 9, 10, 11, 12. It is 1. Okay, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All the numbers are there. So these are the cases. We don't have to use any don't care condition as all the 16 variables are covered in our truth table. So we will consider rest of these are 0. So for TA, if we solve this, we will find this is one pair. This is another pair. We will have BC. And for here it is BC M bar, or here it is M B bar C bar. So we can write this as M XOR with BC. Now if we will solve for TB, for 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8, 9, 10, 11, 12, 13, 14. Okay. So when we solve this, these are 2 quad and this is 1 quad. So from this quad, it is 1, 1, 1, 0. It is 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 0. So when you solve this quad, the equation for TB, we will write equation for TB. I can just erase this. We can write TB equation here only. So for TB, the equation will be, M is not changing. So we will put M, and here C bar is not changing. And in this case, M bar C. So you can say that this is nothing but M XOR with, this is XOR with C. And in case of TC, all ones. So we can say for TC, the equation will be 1. Now if we draw the diagram it will be 3 flip-flops, TB, TA, TC, all are synchronized in nature. So we have same clock, QC, QB and QA are the output. We have equation that TA equation is M XOR with BC, TB equation is M XOR with C, and TC equation is 1. So TC equation is 1, so we connect TC 1, that is logic 1 here at TC. For TB we need an XOR gate. Here we are having M as one value and C as another value. In case of TB, okay, so for this we have B and it is C. So in this way we will have a 3-bit up and down counter. So if any design statement is given to us for designing any binary counter for 4-bit, 3-bit, we will use these sequence or these method to design a binary counter. One more thing, if a mod is given to us, that mod n, if we have to design a mod n, then we have to find the number of flip-flops. So in this 3-bit counter, the mod is 8 as we are going from 0 to 7. So we have 8 different stages. So to design a mod n counter, the relation is if n is equals to number of flip-flops, then it should be greater than or equals to n. So using this relation, we will find the number of flip-flops to design a mod n counter. So this is all about designing a binary counter. Thank you.